Welcome to AI Dispatch, your channel for the latest AI videos on YouTube. If you don't want to miss these updates, please like, subscribe, and share. This video features Max Welling from Latent Space, a deep learning pioneer with a perspective that challenges the entire foundation of how we think about computation. His central thesis: materials, not algorithms, determine the limits of technological progress. He claims that while the industry obsesses over GPU clusters, the fastest computational substrate already exists in the physical laws governing chemistry. His framework reframes laboratories as hardware components and positions material science as the actual bottleneck for civilization's next phase. Max Welling presents a concept that immediately forces a redefinition of what constitutes a computer, the physics processing unit, or PPU. Conventional computer architecture divides processing into CPUs for logic and GPUs for parallel computation. Welling introduces a third category that violates this digital framework entirely. He argues that when a chemist mixes compounds in a laboratory beaker, nature executes a calculation with speed and precision no silicon-based system can match. The molecular interactions occur according to quantum mechanics, instantly resolving forces and bonds that would require prohibitive computational resources to simulate digitally. His position: the experiment is not a test of a hypothesis. It is a query submitted to nature's computational substrate. The lab becomes a processing unit. He envisions automated laboratories functioning as hardware in our compute stack, where instead of writing code to simulate molecular behavior, we physically instantiate the molecules and let physics run the calculation. This transforms the meaning of computation from something that happens on chips to something that happens in matter itself. This reasoning leads directly into his inversion of the software-centric worldview. The dominant narrative in technology holds that software is the apex of value creation, with large language models representing the pinnacle. Welling reverses this hierarchy with a single observation: every piece of software ultimately depends on a physical substrate. An LLM requires a GPU. That GPU is manufactured using specific chemical resists, etched with extreme ultraviolet lithography, and assembled from materials engineered at the atomic level. The software layer is entirely contingent on the material layer beneath it. He applies this logic to energy systems. Solar panel efficiency remains locked at approximately 22%, not because of theoretical physics limits, but because current panels use suboptimal materials. He notes that switching to perovskite-based designs could theoretically push efficiency to 50%. This would double global solar energy capture without constructing a single additional installation. The constraint is not policy, funding, or engineering talent. The constraint is identifying the correct arrangement of atoms. This shifts the entire problem space from optimizing algorithms to discovering superior matter. Welling then describes how this discovery process will operate, and his model contradicts the traditional hypothesis-driven scientific method. Historically, science proceeds through human intuition. A researcher proposes a theory, designs an experiment, and iterates based on results. Welling describes a transition toward what he calls a search engine for matter. Instead of guessing which molecule might solve a problem, you specify the desired properties, and an AI system searches the combinatorial space of all possible molecular structures to generate candidates that meet those specifications. However, he introduces a constraint that directly contradicts the current hype around fully autonomous AI laboratories. The prevailing expectation is that the future belongs to dark labs, facilities where AI agents autonomously design experiments, robotic systems execute them, and humans are removed from the loop entirely. Welling states this vision is premature. His reasoning centers on the irreducible complexity of physical experimentation. Unlike software, where failures are deterministic and reproducible, chemical reactions collapse unpredictably, equipment malfunctions in novel ways, and real-world data contains noise that no simulation captures. He identifies the actual competitive advantage in his company, Cusp AI, as not the AI model itself, but the engineering infrastructure required to connect digital predictions to physical validation. The difficulty lies in building reliable data pipelines from messy, real-world experiments. He maintains that for the foreseeable future, the bottleneck is not AI capability, but the human expertise required to interpret and guide physical processes. The breakthrough will come from chemists wielding AI as a precision tool, not from AI replacing chemists. Welling then applies this material-first logic to environmental problems, arriving at a solution that inverts conventional environmental policy. The standard approach to plastic pollution emphasizes restriction: ban single-use products, tax plastic consumption, reduce production. Welling proposes the opposite: Engineer plastics that self-destruct into fertilizer after a predetermined period. Instead of eliminating plastic, redesign the substance itself so that disposal becomes nutrient cycling. This reframes the object from pollutant to temporary structure with a designed end state. The shift is from behavioral modification to molecular redesign. Finally, Welling connects generative AI to fundamental physics in a way that redefines what these models actually represent. Most people understand diffusion models, the architecture behind image generators like Midjourney, as a statistical technique from machine learning. Welling reveals that the mathematics governing these models is identical to the equations describing non-equilibrium thermodynamics. The process by which an AI removes noise from an image to generate a coherent picture follows the same mathematical structure as heat dissipation in a physical system. This is not an analogy. The equations are the same. This implies that insights from thermodynamics can be directly imported into AI research, and conversely, that AI techniques can solve problems in statistical physics. It suggests a deeper relationship between intelligence and entropy than intuition would predict. However, within this theoretical elegance, Welling offers a practical observation that contradicts the instinct for mathematical purity. In neural network design, there exists a concept called equivariance, embedding symmetries directly into the model's architecture, so it inherently understands that a rotated object remains the same object. This approach is mathematically rigorous and theoretically optimal. Welling admits that, in practice, a cruder method often performs better. Simply training the model on thousands of rotated examples through data augmentation, he explains that enforcing strict mathematical constraints can create a complex optimization landscape, making it harder for the model to converge to an effective solution. The lesson: when compute and data are abundant, brute force frequently outperforms elegant theory. The mathematically perfect solution is not always the empirically superior one. Welling's analytical method exhibits a consistent structure. He systematically dissolves the boundary between digital abstraction and physical reality. He treats nature as a computational resource, materials as the foundational layer beneath all software, and the equations of thermodynamics as the blueprint for artificial intelligence. The central question his framework raises: if we can genuinely query the physical world as a search engine and engineer matter with the same fluidity we currently engineer code, how rapidly will the material basis of civilization itself transform? If you're interested in the video featured in this episode, click the link below to watch the original.